For decades, Pluto seemed like the forgotten corner of our solar system. It was tiny, incredibly distant, and almost impossible to study from Earth. When it was discovered in 1930, scientists believed they had finally found the mysterious ninth planet they had been searching for. Pluto quickly became famous. It appeared in schoolbooks, astronomy charts, and countless illustrations of the solar system. Then everything changed. In 2006, Pluto was reclassified as a dwarf planet. For many people, that decision made Pluto seem less important. It became the small frozen object beyond Neptune, a distant remnant orbiting in almost complete darkness. But the more closely scientists have studied Pluto, the harder it has become to describe it as a simple frozen rock. The spacecraft New Horizons transformed our understanding of Pluto when it passed the dwarf planet in 2015. Instead of finding a featureless ball of ice, scientists discovered mountains, enormous plains, strange ridges, glaciers made from frozen gases, and a thin atmospheric haze. Pluto had landscapes. It had weather. It had chemistry. And it was changing. The James Webb Space Telescope has added another layer to that story by allowing scientists to study Pluto's faint light and atmospheric chemistry in extraordinary detail. Webb cannot travel down to the surface like a spacecraft, but its instruments can examine the fingerprints left by molecules in Pluto's atmosphere and surface environment. Those fingerprints reveal a world far more complicated than the old image of Pluto suggested. One of the strangest parts of Pluto is its atmosphere. Compared with Earth's atmosphere, it is extremely thin. Nitrogen makes up most of it, with smaller amounts of methane and carbon monoxide. At first glance, there seems to be almost nothing there. But even this extremely weak atmosphere interacts with sunlight. High above the surface, sunlight breaks apart methane molecules. The resulting pieces can combine into larger and more complicated hydrocarbons. Eventually, some of these particles become part of the hazy material surrounding Pluto. That haze gives Pluto its mysterious appearance. The particles are also important because they influence the temperature of the atmosphere. Instead of simply trapping heat, Pluto's haze can help radiate energy away into space. The atmosphere can therefore become even colder. This creates a remarkable situation. A world that already receives only a tiny fraction of the sunlight reaching Earth has an atmospheric system capable of helping it lose heat. Pluto is cold beyond ordinary human experience. At its surface, temperatures can become low enough for substances that are gases on Earth to exist as solid material. Nitrogen can freeze onto the ground. Methane can become ice. Carbon monoxide can also freeze under the right conditions. The landscape is therefore not merely covered in ordinary water ice. Pluto's surface is part of a constantly changing chemical environment involving several different frozen substances. And some of those chemicals become something even more interesting. Complex organic compounds can form when methane and other molecules are altered by sunlight and radiation. Among these materials are substances known as tholins. Tholins are not living organisms, and their presence does not mean Pluto contains life. But they are chemically fascinating because they contain carbon-rich compounds that resemble some of the complex chemistry scientists study when investigating the early stages that can precede biological systems. On Pluto, however, the process occurs in an environment where almost everything eventually freezes. The chemistry can continue, but the extreme cold slows everything dramatically. Instead of becoming part of an active biological environment, these compounds can settle onto the surface and remain preserved for enormous periods of time. That makes Pluto resemble a gigantic natural laboratory frozen in deep space. But Pluto's story does not end with its atmosphere. Its largest moon, Charon, appears to be part of the same chemical system. Charon is enormous compared with Pluto. The two bodies orbit a common center of mass, creating one of the most unusual planetary systems in the solar system. Pluto's weak gravity allows some atmospheric particles to escape into space. Some of that escaping material can eventually interact with Charon. Methane is particularly important. Material originating from Pluto can travel across the space between the two bodies and become deposited on Charon's surface. At Charon's poles, sunlight and radiation can then transform those molecules into darker, more complicated compounds. This helps explain why parts of Charon have a striking reddish appearance. In other words, Pluto and Charon are not completely isolated worlds. They can exchange material. One world loses molecules. The other can collect them. Radiation changes the chemistry. And over enormous periods of time, the results become visible on the surface. The system may look quiet from billions of miles away, but molecular activity continues inside it. Pluto's surface is equally surprising. These formations are unlike ordinary snowdrifts or mountain ranges. They rise dramatically above the surrounding terrain and create a landscape that looks almost impossible. The structures may have formed through processes connected with Pluto's atmosphere and long-term climate cycles. As methane moves through Pluto's environment, sunlight and temperature differences can gradually reshape the surface. The deeper scientists look into Pluto, the more difficult it becomes to separate the dwarf planet from the larger mystery surrounding the outer solar system. Pluto is only one object in an enormous population of icy bodies beyond Neptune. That means every discovery there raises another question. If a small world like Pluto can have an atmosphere, complex chemistry, active geology, and possibly an underground ocean, what might be happening on the countless objects we have never examined closely? For decades, planetary science focused heavily on the major planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune were the obvious targets. They were large, bright, and comparatively easy to observe. The distant icy objects were different. They were faint. They were small. They moved slowly across the sky. And because they were so far from the Sun, scientists expected them to be relatively simple. Pluto changed that expectation. Its surface revealed that extreme cold does not necessarily eliminate geological activity. Instead, it can create an entirely different kind of planetary behavior. On Earth, water controls much of the surface. On Pluto, nitrogen, methane, and carbon monoxide can become part of the landscape. These substances can freeze, evaporate, migrate, and redeposit as the dwarf planet moves through its enormous orbit. That creates a strange form of weather. There may be no rainfall in the familiar sense, but materials can still move between the atmosphere and surface. During colder periods, atmospheric gases can settle onto the ground. As Pluto receives more sunlight, some of that material can return to the atmosphere. The entire process can repeat over timescales far longer than a human lifetime. A person could live their entire life on Pluto without witnessing even a small fraction of one complete seasonal cycle. Yet the cycle is real. The surface is constantly responding to changes in sunlight. This is one reason Pluto's atmosphere is so important. It connects the sky with the ground. The atmosphere is not simply a layer surrounding the dwarf planet. It participates in the transformation of the surface itself. Methane rises into the atmosphere. Sunlight changes its molecules. New compounds form. Some eventually fall back down. The surface receives material from above while simultaneously sending gases back upward. It is a slow chemical exchange between Pluto's ground and sky. And the process does not stop there. Radiation from space constantly interacts with the molecules covering Pluto and Charon. Because there is no thick atmosphere to block much of that radiation, the surface remains exposed to an environment that is extremely harsh by terrestrial standards. Over enormous periods of time, radiation can alter molecules and create new compounds. The result is a surface that acts like a chemical archive. Every layer can preserve clues about Pluto's past. The dark and reddish regions may contain material that has been transformed for billions of years. The brighter areas can tell a different story. Some regions are covered with relatively clean nitrogen ice. That ice can move slowly across the surface, behaving almost like a glacier. On Earth, glaciers are driven largely by gravity and temperature. On Pluto, frozen nitrogen can behave in surprisingly dynamic ways despite the extreme cold. The famous heart-shaped region, Sputnik Planitia, is one of the clearest examples. It is a vast basin filled with nitrogen ice. Scientists have found evidence that the ice can circulate. Material in one area may gradually sink while warmer material rises elsewhere. The process is extremely slow, but it means Pluto's surface is not necessarily a permanent frozen shell. The ice itself can move. That discovery was important because it showed that even at temperatures far below anything humans experience naturally, materials can remain active when given enough time. But Pluto's most important secrets may not be on the surface. They may be hidden underneath it. The possibility of an internal ocean has been investigated through Pluto's shape, geology, and orbital history. A subsurface ocean would be difficult to detect directly. There is no spacecraft currently drilling through Pluto's crust. Instead, scientists look for indirect evidence. They examine fractures. They study mountain formations. They analyze the orientation and age of surface structures. They calculate how Pluto's interior could have evolved. Every clue helps determine whether liquid water might still exist below the ice. If an ocean is present, it would not resemble Earth's oceans. It would be buried beneath a massive layer of ice. The pressure would be enormous. The temperature would be extremely low. Its chemistry could be completely different from the water environments familiar to us. And yet, liquid water beneath an icy world would be scientifically extraordinary. It would demonstrate that potentially habitable environments may exist far from the warmth of the sun. That idea becomes even more interesting when Pluto is compared with other icy bodies. Europa, one of Jupiter's moons, is believed to contain a global ocean beneath its frozen crust. Enceladus, orbiting Saturn, has also shown evidence of a subsurface ocean and active plumes. These worlds are much closer to the Sun than Pluto, but they demonstrate that internal heat can matter more than sunlight. Pluto could represent another version of the same phenomenon. Its energy would come from inside rather than from the weak sunlight.